Now see applications of Gauss's theorem. First one is field due to an infinitely long straight uniformly charged wire. Suppose you have got like this is your uniformly charged wire and linearly here there is charge distribution is linear. This is infinitely long thin wire. Now if you want to calculate electric field at this point, suppose at a distance r, if you want to calculate electric field. So first we take the 2 points here, one is over here and one is over here at a equidistance from this center, and by taking this radius r we draw a cylinder here which encloses this much length of this charged wire, L length, and let lambda is linear charge density, linear charge density. So we have drawn, this is here a Gaussian surface which is enclosing L length of this charged wire here. So now there are the three surfaces, one is this topmost surfaces here, this circular part, and one is this is here curved surfaces. So every point here the electric field's direction is this side here. Let us here take area vector, that is here ds, also here we can take ds1, and this side area vector is here we can take suppose ds2, and this side is also here we can take ds2. Now electric field is over here. Now between area vector and electric field the angle is 90 degree here. So the flux through this surface and this surface is equal to 0, but the electric flux through this curved surface of this cylinder is not 0. So basically here the flux is contributed by only here the curved surface of the cylinder. So we can write in this case the total flux here E dot ds is equal to E dot ds1 plus E dot ds2 plus E dot ds2. This is the total flux and this through the disclosed surface. Now we can write here E ds1 cos theta plus E ds2 cos theta plus E ds2 cos theta. So in this case theta is 90 and in this case also theta is 90, these are the two surfaces here. So the flux through these two parts will be equal to 0. So now in this case theta is equal to 90 and this is also theta is equal to 90. So these two parts are equal to 0. So we will be getting here total here E ds1, here theta is equal to 0. So we can write E and integration of ds1 is equal to E into 2 pi r L. So this is the total flux through this Gaussian surface which we have chosen, that was cylindrical one. Now according to Gauss theorem, we can write total flux through the closed surface is equal to q by epsilon naught, q net, that is the total charge enclosed by the surface, and now here lambda was the charge density we have already taken. So we can write here lambda into L upon epsilon naught. So if you equate this and this, we will be getting here E into 2 pi r L is equal to lambda L upon epsilon naught, L and L will get cancelled. So E is equal to lambda upon 2 pi r epsilon naught. So in this case here we can take also vector form here, this is r unit vector, that is outward, if it is the positive charge, and if it is negative charge, that is here inward. So now this is the electric field intensity due to linear charge distribution at a distance r. So we can also write here E is inversely proportional to r. So by using Gauss theorem we have calculated electric field intensity here. So, see here second application of Gauss theorem, we have to calculate field due to a uniformly charged infinite plane sheet. So, we take here thin plane sheet of the charge, where the positive charge is distributed here. This is very thin sheet, so this positive charge appears both sides of the sheet. This has got sigma surface charge density, Now, from symmetry, we can take electric field perpendicular to the plane of this sheet, both the sides, and at an equal distance electric field will be having same magnitude also. So, suppose if you are taking this much part of this sheet, which is enclosed by drawing a cylinder, and this cylinder is piercing into this sheet here. So, this whole distance is here 2r. So, this side is r and this side is r. At this point we are taking same electric field and perpendicular to the sheet here like this direction, and here it is here this side. So, this is here the Gaussian surface drawn here. Now, so we can take one area vector to this side, that is ds1, and another area vector to this side, that is also ds1, and one area vector to the curved surface, that is ds2, and electric field is here every time perpendicular to the sheet here and outward. So, now we can calculate total flux. Total flux is equal to vector E dot ds1, this and this, there are both the E dot ds1, so we can take twice, plus vector E dot ds2. We can write twice of E ds1 cos theta plus E ds2 cos theta. Here theta is equal to 90 degrees, so there is no flux through the curved surface of this cylinder. So, here theta is equal to 0. So, we can write here total flux E dot ds is equal to twice of E, we can take common because E is constant at these points, and integration of the ds1 we can take here this one. Suppose it is the area we take here A, so we can write twice of EA. So, total flux through this surface and this surface is equal to twice of E into A. So, now total electric flux through the Gaussian surface is this much 2E into A. Now, we can write according to Gauss theorem, total flux E dot ds is equal to Q upon A epsilon naught, net charge enclosed in vacuum here, that we can write sigma into A upon epsilon naught. Sigma is the charge density. If you equate these two, you will be getting twice of EA is equal to sigma A upon epsilon naught, this will get cancelled, E is equal to sigma upon twice of epsilon naught. So, we can write E vector is equal to sigma upon twice of epsilon naught. Here we can write here n cap. N cap is here perpendicular to the sheet and in outward direction. So, this is the electric field here, which is independent of actually the distance here, which basically depends on the charge density. So, we have calculated electric field intensity due to thin plane sheet of the charge using Gauss theorem. So, now third application of Gauss theorem, that is a field due to a uniformly charged thin spherical shell. Suppose there is a spherical shell which has got charge q and radius is here, suppose it is r. Now, if you want to calculate electric field intensity at a distance r here, it means here we can take r is greater than r. So, if you want to calculate electric field intensity at this point, by taking this radius r small r, we draw a sphere that is known as Gaussian surface. And Gaussian surface is drawn in such a way that it does not pass through this charge or through this shell, and it is enclosing completely the shell, and now we just take area vector at any point. Suppose you have taken area vector is here, that is ds, and electric field is also radially outward. So, we can write flux is equal to E dot ds is equal to E ds cos theta. Here theta is equal to 0. So, we can write E ds, and here we can write E is constant at every point on the Gaussian surface. Here we write integration of ds, that is a whole surface. So, that is E into 4 pi r square. Now, according to Gauss theorem, this flux can be written E into 4 pi r square is equal to q by epsilon naught net charge enclosed by this Gaussian surface. So, in this case we can take E is equal to q by 4 pi epsilon naught r square. Here vector, this is r unit vector. So, this vector is radially outward. So, this is the electric field intensity at any point at a distance r from the center, which we have calculated by using Gauss theorem. But see, this electric field intensity is equal to the electric field intensity due to point charge. It means we can say this spherical shell is behaving as a point charge. So, in the first case we have taken, we have seen here when r is greater than r, it means point is somewhere here, and we calculate electric field intensity at this point. We have got E is equal to q by 4 pi epsilon naught r square. Now, if you take r is equal to r, then electric field intensity will become q upon 4 pi epsilon naught r square. So, on the surface of this cell is this much. Now, if you are calculating third point here, r is less than r, it means point is somewhere here r, and by taking this you are drawing here the Gaussian surface. You will see here all the charge is outside this Gaussian surface. So, no charge is enclosed by this Gaussian surface. See, if you are drawing Gaussian surface inside the cell, so net charge enclosed by the Gaussian surface is 0. Therefore, electric field intensity inside the cell is 0. So, when r is less than r, we will be getting E is equal to 0. So, we can show this variation of E from the center of the shell with the help of the graph. We can draw the graph like this. This is your x axis, this is y axis. Here we have taken E and here is r. This is the O is the center of the sphere. When we start moving from the center of the spherical shell, so at r is equal to r, electric field is here this much, maximum, that is equal to this much here. When we go beyond this surface, electric field intensity reduces here because E is proportional to 1 upon r square. So, the graph is like this. So, outside here, that is E is proportional to 1 upon r square. So, this is the variation of electric field intensity with the distance r from the center of the spherical shell.